Behind me, you can see heavy snowfall in Kiel. If you want to watch that.
Okay.
So, yeah, let's start. My paper is about, or first, let me thank the organizers for inviting me to this interesting event. I'm very happy to be in Japan, at least virtually today. The paper I'm going to present to you is about estimation of agent-based models. That means of models that describe the interaction of a large crowd of agents, as we see in this old cartoon from the Financial Times about financial crisis, bubbles and crashes. And the methodology I'm going to present to you is one that has not been used so far as I know, in economics, but it's actually very popular, as I learned, in ecology, where you also have a brand of agent-based models. It is called ABC, excuse me, Approximate Bayesian Inference, and it provides a very general framework that is universally adaptable to any kind of agent-based models. What I'm going to present to you is the principles of this ABC inference and a worked out example for how to apply it in a kind of baseline agent-based model of interaction in a financial market. There is a certain literature already. Let me shortly go through that on estimation of agent-based models. The earliest contributions stem from the early years after 2000. I think the first one is Gilly and Winker, simultaneously with Westerhoff and Reitz. They apply different methodologies. For example, a number of papers kind of construct agent-based models that are similar to certain well-known statistical models in their formal structure, like star models or arch models. And then, of course, you can apply the methodology of these models that has been developed in econometrics. Later on, simulated method of moments has become pretty popular. There's a whole chain of papers by Rainer Franke, my former colleague here at Kiel, and Franke and Westerhoff. I have recently, alone or with co-authors, applied other alternatives like numerical maximum likelihood approaches and generalized method of moments, etc. There are only a few papers that use Bayesian estimation. Typically, you have a frequentist approach. The first one, to my knowledge, is Grazzini, 2017, who uses actually already a very simple variant of approximate Bayesian computation for a medium-scale macroeconomic model. There is Bertschinger, who uses what is called Hamiltonian Markov chain Monte Carlo, which, however, is also not universally applicable to all kinds of agent-based models. And in some recent papers, I have applied both frequentist and Bayesian methods, namely the particle filter or adaptive Bayesian estimation for simple financial agent-based models. You can find a survey that is not yet completely outdated by Remkos-Winkels and myself in the Handbook of Computational Economics. Of course, this field is rapidly developing, but 2018 is not too far in the past, so it is certainly to a certain extent still relevant and should give you an overview over what has been developed up to that time. As I said, ABC, except for the contribution by Grazzini, has never been applied in economics, but it's generally applicable. It's actually the Bayesian counterpart of a method of moments, because it requires no likelihood, but just the ability to simulate a model and to extract information on certain functions, moments, however you would like to call it, of the model. The nice feature about this approach is, however, that although it is very simple, there are quite a number of theoretical insights, which kind of is in contrast to other more heuristic approaches. So we know a few things about the outcome of such an ABC estimation exercise. Namely, it has been shown that you have posterior concentration at the true value if the sample size is large enough. And it has been shown that the posterior mean that you obtain from ABC is asymptotically equivalent to the point estimates that you obtain via GMM if you use the optimal weight matrix. So in a sense, it's superior to frequentist GMM because it is equivalent to the best you can get with a GMM approach. And it actually provides a rigorous underpinning of what has been denoted pattern-oriented modeling. That's a term that you find often in the sociological, ecological, agent-based literature. And it basically means that you take some moments, some functions, some patterns in order to identify the parameters of a model. That's a very loose kind of concept. Of course, the econometric and statistical counterpart is GMM or SMM, moment-based estimation in a frequentist context, or approximate Bayesian computation if you take a Bayesian viewpoint. So what is it about? You define an objective function that is composed of the differences of moments between empirical and simulated data, which I call rho of S set and SY. S set and SY are the summaries for the simulated data and for the empirical data, and rho summarizes the differences. So that's pretty much what you do in a GMM or SMM approach as well. However, this is Bayesian, so you start with generating data from a prior distribution, but I will take in my examples very general prior distributions, and you accept samples that are having summaries that are sufficiently close to those of the data. That means you start with a criterion for how close the summary should be, the moment function should be, the aggregated moment function should be to the data. And you accept all those. I should be able to write into that, but I'm not getting it. Oh, it doesn't, yeah. You accept those empirical samples indicated by set. You accept, excuse me, those simulated samples indicated by a set that are sufficiently close to the empirical samples, namely that fulfill this criterion that the difference between both in aggregate should be smaller than some pre-specified value epsilon. And those selected samples then would give you the posterior distribution. So it's a very straightforward approach applied for the transition from the prior distribution to the posterior, based not on a likelihood, but based on these differences of summaries. And this is computationally very easy to implement. Yeah, you simply repeat the simulations as long as it takes you to find enough samples that are close enough to the empirical data in their moment or pattern behavior, if you like to call it like this. So more formally, that means that the accepted samples are distributed according to these posterior here. Yeah, it's a standard posterior, yeah, as you can find it in the Bayesian literature, but it replaces the likelihood by the accepted samples. Yeah, so here you have the prior distribution, you have the function that describes the likelihood of the simulation under the parameters, and you have the indicator function that this is applied only to those samples that are accepted. Yeah? So these samples give you then the likelihood of the parameters and the simulations under the observed moments. And the posterior of the parameters then is obtained because that's the joint posterior of the parameters and the simulation. The posterior of the parameters itself under the moments is obtained as the integral over the simulations, but that simply means that you count the number of cases that lead to a certain parameter value. Yeah? This serves as an approximation for the posterior conditional on the moments, yeah, because you don't fit the moments exactly, you only fit a neighborhood of the moments that you observe in the empirical data. What in principle you would like to have is a posterior conditional of the moments if the moments are satisfied exactly. That means if epsilon is equal to 0, but you won't get that. So you have to work with a neighborhood, just as you have in GMM and SMM in frequentist estimation, because the moment conditions will never be exactly fulfilled. The moments will never be exactly the same in the simulations like in the empirical data. So that's an approximation of what you are after. And this posterior based on the moments itself is an approximation of the posterior based on the data. Yeah, because the moments is what you are working with, pretty much like in SMM. You estimate the parameters based not on the data itself, because for that you would need the likelihood, but based on the description of the data by a certain set of moments or patterns. But this is exactly what typically we want to do for agent-based models. So this rejection sampler yields the posterior conditional on the moments. It is equal to the posterior conditional on the data, in fact, if the moments are sufficient statistics, but this, of course, is not normally the case because that only holds for exponential distributions. But again, it can be shown that you would have posterior concentration at the true value in the large n limit. That means if you have a large number of data, if the moments satisfy at least an identifiability condition. And this is typically tacitly assumed, although it is not guaranteed sometimes in agent-based models. And if the summary satisfies such a central limit law and the threshold decreases appropriately with the data, then in fact the posterior can be shown to converge in distribution to the exact posterior under the moments. So there's a lot of theoretical knowledge, yeah, which is always good because you should know what you are doing if you estimate something. Yeah, you should know that the estimator would converge theoretically to the right true values. The major drawback is the computational burden here, yeah, because you can imagine that if you impose such a condition here with a very small deviation that you want to have between the empirical and the simulated moments, you have to simulate maybe millions or more of samples in order to get a decent number of acceptances, yeah, say 100 or 1000. So there's a huge computational demand here in this naive approach, which is called the rejection sample and was the first proposal of an implementation of this approximate Bayesian computation. You can do better, of course. You can design, and there's a large literature on that, computationally more efficient ABC algorithms. And basically what you do to achieve that is to combine it with sequential Monte Carlo. That means you use intermediate distributions between the prior, which is pretty uninformative mostly, and the posterior that at the end of the day you want to arrive at. Yeah, so you create a stepwise transition from the prior distribution to the posterior. And this is what typically is done by SMC. There are a number of approaches that appeared about 10 years or a bit longer ago that provide different alternatives to how exactly do that. You define different thresholds, yeah, epsilon t, and t is then the round, so to say, the iteration of the methodology. And in every round, you decrease epsilon t, yeah, and you propagate a set of realizations or particles for the parameters from the prior distribution through these intermediate steps to the posterior, which typically should be, and I'm going to show you simulations of that, much more computational efficient than the naive approach. So it is the baseline ABC typically combined with a baseline more or less sequential Monte Carlo approach. So what would it look like? It now looks more complicated. This ABC SMC in a typical implementation what you have is you have a decreasing sequence. This decreasing sequence is either pre-specified, yeah, that means you take the endpoint, how close you want to get to the empirical moments, and then you define from the prior distribution, maybe the starting point, how far the prior distribution is away from the moments, and you kind of define a decreasing sequence with equidistant maybe epsilons, yeah? And you try to get closer and closer to the thought posterior step by step. Then in the first step, you would do the same as in the naive approach. You draw particles in the sense of set of parameters from the prior, yeah? You generate simulated data. You compute the difference between the moments of the simulated data and the empirical data. You choose only those, or you keep only those that are smaller than the first threshold, which still should be relatively large, yeah? And if you have a complete sample, say of capital N, 1000 in my applications, or 100, whatever is practical, then you assign weights to them equal to 1 over n. And then the iteration starts. Yeah? So that's a typical creation of particles and evaluation of the particles. And this pool of particles that are already relatively close in their moments to the empirical moments then serves as the pool for the next generation. There's somehow a transition kernel that can be defined in a different way, by which you create the new population of particles from the previous one, yeah, via some stochastic disturbance. You can use a random walk disturbance whatsoever. This should be the most straightforward application. And since the parents, so to say, are fulfilling this condition here, the offspring that you get from this transition kernel typically should also not be too far away. And so you have a higher likelihood to meet such a condition than from the prior distribution. You again evaluate the difference between the so generated new simulated data and their moments to the empirical moments. You impose a stricter requirement, a smaller epsilon t, and select again in the next step those that fulfill this stricter requirement. Then comes a step where you have to assign weights. This is a bit complicated. I'm not going into the details. The weights have to take into account the ancestry, so to say, of each one of these members of the new pool of particles of parameter sets. Yeah, so that you properly take into account the likelihood of each one of these generated samples via the sequential Monte Carlo approach. So you go stepwise, and that should provide, and in fact it does provide a huge saving of computation time because you approach gradually the posterior distribution that you are after. Yeah. So these are generations, just like in the genetic algorithm, generations T2 to capital T. It's kind of importance sampling with random variation. Yeah. There are different variants for that. In the literature, I tried a number of those. You can also keep a fraction alpha of the particles of the previous round. You can use Markov chain Monte Carlo steps instead of the transition kernels. You can perform even a number of independent Markov chain Monte Carlo sets draws in order to create the new particles, etc., etc. Yeah. So there are different methodologies here, different kind of particular implementations of the sequential Monte Carlo step in this algorithm. What is important is that you don't typically take the resulting posterior as such, but since you have finite deviations of the moments between the empirical and the simulated data, you adjust the final posterior by something like a regression. The simplest one is a linear regression. Yeah, you simply extrapolate from the case of finite differences of moments to the case of no difference. How would the parameters look if the moments would be exactly the same between the empirical and the simulated data? So that requires, in the simplest of cases, there are a number of alternatives for that, just a linear regression. Yeah, you compute the dependency of the parameters on the deviation, as I is the summary, the aggregated moments for the parameters at I, yeah, simulation number I. You compute the deviation of the moments from the empirical moments of that simulation, and then you perform a regression for all the simulations of the parameters on the difference between summaries or moments. Then hopefully you get some systematic part plus some random deviation. Yeah. And if you have identified the slope and the intercept of this regression, you can adjust the parameters accordingly. And that would be your final posterior, yeah, that adjusts or extrapolates towards the point where there would not be any deviation between the simulated and the empirical moments anymore. Yeah. Basically, what that is the estimated mean plus the random deviation. Yeah, because you control for the systematic deviation here between the simulated and the empirical moments. A popular alternative is via a nonlinear heteroscedastic model. I also tried that, where you allow for different variances of different sets of moments, and you also estimate a second equation for the variance. Yeah. But in my example, I found that this was not providing any additional improvement of the posterior. There are additional variants that are more elaborate. You can use even neural networks, you can use rich regressions, etc., in order to implement this step of the regression adjustment. That's pretty common. So you find in all the applications of ABC, basically in biology where it's mostly applied, this step as a routine kind of implementation. So that's it. That's the principle of this methodology. And what I'm going to present you shortly in the rest of the talk is an application to a model that I have been using often as a test case. So I know how other estimators behave for this model. It's the model of Alfarano et al. Alfarano, myself, and Friedrich Wagner, a former colleague of mine here at Kiel, that has also been used by others. It's one of these very simple agent-based financial market models. We have two opinions or strategies. We have optimists or pessimists. The optimists and pessimists are allowed to switch to the other group. So a pessimist might become an optimist with a probability pi plus at time t, and vice versa with pi minus at time t. That's depending on the number of optimists and the number of pessimists. So it's relatively pure herding behavior. A and B are parameters for idiosyncratic changes, and B for the influence of herding behavior. We can summarize then the overall aggregate attitude of the agents, whether they are more bullish or more bearish, by this index xt, which is the number of optimists minus the number of pessimists. The optimists, of course, will be buyers. The pessimists will be sellers. And then we bring that into an asset pricing framework in the following way. Here we have the difference between optimists and pessimists. If positive, that's a positive component of excess demand. If negative, there's more supply than demand of this group. And on top of that, we have some traders who follow a fundamentalist strategy. That means they buy if the price is lower than the fundamental value and vice versa. Beta is the price adjustment speed. So pretty conventional, a very, very simple model, standard asset pricing model from the behavioral finance literature, plus this agent-based model of herding among the group of noise traders, chartists, whatever you would like to call them. If you have market clearing, then you get the following law for returns. Returns follow the fundamental innovations, UFT. So returns reflect the changes of the fundamental value, which bring in a new parameter sigma f, the variance or standard deviation of the fundamental innovation, and they are driven by the changes of the composition of the noise trader group. If there are more optimists than before or more pessimists than before, then there will be more demand or more supply. That means returns will go up or down because of market pressure. So this is a very, very simple model. And we want to estimate some of its parameters. Why do I use that? Now, I use it because it's a true agent-based model. When I simulate this model, I really simulate an ensemble of agents. There's no shortcut. It's really an ensemble of, say, 100 or 1,000 agents that are switching back and forth between optimism and pessimism, bearish and bullish behavior, according to the rules on the last state. Yeah. The aggregate state of this model changes with the distributed changes of all its members. So there's, in fact, randomness at the level of each agent, because each agent is following a probability for changing her or his attitude. And this model is well known to be able to generate the stylized facts of financial markets, namely fat tails and clustered volatility. So that's what you see here. Yeah. This is the opinion index, and this is a simulation of the returns, and the returns show clustering of volatility. So it's pretty close to empirical data. For the estimation, I use a set of moments. I think I have to speed up. Squares and absolute values of returns and autocorrelations of the squares and the absolute values. And I use a GMM type of summary functions, which uses as the weight factor the variance-covariance matrix of the empirical moments. So that's pretty close to GMM. We set n equal to 1,000, so that's the number of particles, and we use this sequential Monte Carlo ABC approach. The parameters are given like this. So that's a standard set of parameters that leads to empirically nice time series, A and B for the agent-based model, and sigma f for the standard deviation of the fundamental innovation. What you can see is that for different models you have, or for different methods of, I used here simply the names method 1, 2, 3, 4. For method 1 is the original one. Yeah, you have very different computational needs. Yeah, for this one here it's 25,000 seconds. For this one here it's only 500 seconds. So that shows the improvement, so to say, in efficiency via SMC compared to the naive approach. I skip some of the features here. There are some Monte Carlo results that show you how close typically the estimated parameters get to the empirical ones, but they get close actually only after this regression adjustment. Might it be the original or the heteroscedastic one? The parameter estimates without this adjustment typically are further away from the true underlying data. So you see how important that is. And again, you see here the time needs for different methods are very different. And of course, since the quality here is pretty much the same, we choose the one that is more efficient by one order of magnitude. I have experiments with alternative distance functions in the paper, but I skipped that because they were all not better than the one that I have introduced before. Another advantage of this methodology, or another kind of achievement that you can get, is that you can also use it very shortly for filtering. Yeah, you can use the distance in order to filter the realizations of the hidden variable. The hidden variable here is what I called X before, namely the average opinion, the sentiment of the market. And you would filter that over time by using your simulations, computing the difference between the simulations and the empirical data, and weighting the hidden data with the difference. The realizations that have a smaller difference then would get, of course, a higher weight. And using that would be an alternative to weighting via the likelihood function. Yeah, it's straightforward. It can be used as a kind of side result from the previous estimation exercise. And in fact, here again, we have theoretical knowledge, namely, it can be shown that these ABC filters, or the ABC prediction based on this filter, is as accurate in the limit as exact predictions. Here's a comparison, but I show you better an illustration here. The red line is the hidden variable, which I don't see, yeah, in the estimation, but of course, since I have simulated it, I know it. And the other, the blue and the dark black broken lines show you the filtering of these time series, yeah, the indirect recovery of this time series via the ABC filter and via the optimal particle filter that uses the likelihood. And what you can see is that both are performing almost in the same way. And they track very closely the development of the underlying hidden variable. So you can identify hidden variables in this way as well. You can work with models that have incomplete information on the underlying, on the time series underlying. I have an empirical application here to the S&P 500 over its whole lifetime, almost from 1928 to 2020, which of course is heroic. What you find is that, of course, you get some estimates. The important point is that you find that not all of it is explained by fundamental variation. Yeah, fundamental variation explains part of it, but not all of it. So there is a significant influence of the behavioral parameters A and B that shape the development of sentiment of our agents. So pretty much half of the dynamics then, if you translate it into contributions, is explained by sentiment. Half of the dynamics is explained by fundamental values. The last feature here, and then I stop, you can also use this methodology in order to design a misspecification test. The misspecification test is based on this regression adjustment, because under the hypothesis that the model is correctly specified, the regression adjustment for the simulations should be the same, or should have the same distribution like the regression adjustment for the empirical data. So that is the regression adjustment for the empirical data. I simulate many times a similar regression adjustment for simulated data. I take the 95% point for these simulations, which for two different variants here is 0.8 and 0.9. And since I see that for the empirical data, the variation in this regression adjustment in the simulations is not exceeded, I can actually not reject that this is the correct specification. Yeah. Interestingly enough, I can reject it. I skip that. I can reject it for other sets of data, yeah, for 11 moments, for other sets of moments, excuse me, for 11 moments, this is clearly rejected here. This is much higher for 15 moments as well, yeah, but not for 7 moments. And that shows you that there are some subtle differences between the data and what my model can explain, which is natural because the model is a very simple one. Yeah, if you have a small set of moments, it seems to fit well. If you take a larger set of moments, you see its deficiencies. So I think I have almost exhausted my time. Here you see how it fits the S&P 500 in terms of the sentiment index that you filter out. But I should not spend too much time on that, but come to the conclusions. Basically, what I try to convey is that this methodology provides a very rigorous Bayesian framework for things that are often used in a more heuristic fashion in many ABM papers. You find many ABM papers where you have a similar approach, but it's not rigorously embedded into a statistical framework of which we know its statistical properties. Yeah, this is basically this pattern-oriented modeling, yeah, which tells you that you should choose certain patterns in order to estimate the data. What I would have liked to show you also is some macroeconomic applications, but we so far never were happy with applications to macroeconomic models. But I think this is a completely different story because in macroeconomics, you have so few data points and comparably many parameter values that estimation, in fact, is pretty heroic anyway. Okay, thank you.